Okay, so hope everybody's doing well. We're going to start a new unit, probably one of the last ones for the year, just on geometry to really help students have kind of a head start as they do geometry next year. Some students obviously might be doing it on ALEX, so this might be a little bit of a review. And today we're going to start with the Pythagorean theorem, kind of a long first name. Whoops, I keep doing that, sorry. Long first name. But a really important, one of the really big theorems in all of geometry dealing with right triangles, or triangles where there is a right angle or a 90-degree angle. So there's a lot of different ways to prove them. In the spirit of trying to keep this as simple as possible, there's a little bit of a graphic here where you see these squares, right? These squares, a squared, b squared, and c squared, and they come together to make this triangle in the middle, and specifically a right triangle. And it doesn't matter what size squares you have, as long as they can make a right triangle that connects. Again, maybe it is helpful to do it in a red. This right triangle, as long as the sides connect, then we can say the following. This formula right here. And so this is the Pythagorean theorem. A squared, so a side squared, plus this side squared, b squared, equals this side squared, c squared. This side is called the hypotenuse. Hypotenuse. There is only one hypotenuse in a right triangle, and it is always opposite the right angle. So you can think of this as A is a side, B is a side, and C also a side, but this is always the hypotenuse. So a new word, and there's the spelling. And that's pretty much it. So as long as we might have both sides, and we have to find the hypotenuse. We might have one side. Maybe we have side A, and they give us side C, and we have to find side B. So let's try a few. Oh, by the way, if you see this video, there's a video down here at the bottom, which if you want to copy, this is quite the interesting code here, but that might show you kind of another visual of how the Pythagorean theorem was derived. Okay, so let's try a few of these. I think it's super helpful to always label, and since these are all in blue, I will label in red. Which side is A, which side is B, and which side is C, because our formula depends on where A, B, and C are. After you get the hang of it, you don't need to label it, but I think it's helpful to begin with. So I notice there's my right angle, so I know the side opposite is C. I think that's the best way to always make sure you know what side is C. So I'll label this side A and this side B. Once you have C, A and B, it doesn't matter. I could have labeled the 9 here B and the 12 A, but and it won't matter. So I know A squared plus B squared equals C squared, so 9 squared plus 12 squared equals C squared. 9 squared is 81 plus 144 equals C squared. I'm running out of room, so I'll come down here. C squared equals the 81 plus the 144. That's 225. Now, as you'll recall, in order to get C by itself, so this is still C squared, I need to take the square root of both sides. And that is 15. So this side here is 15. Okay? You should be able to do square root of 225 in your calculator, and that's a whole number. Here again, I see right angle. I'm going to go straight across and label this C. So now it doesn't matter. The 7 can be A, and this can be B. If you wanted to do the 7B and 24A, that's fine. But this side right here, this is C. That's super important. And we don't know what C is. So the theorem says 7 squared plus 24 squared equals C squared. So this is 49 plus 24 times 24 is 576 equals C squared. So now I'm going to have 625 equals C squared. Take the square root of both sides to get C by itself. And the square root of 625 is 25. And that comes out to a whole number. There's going to be some later where we're going to use our reducing or simplifying radicals. Let's try one more. And what I notice that's different here is when I look at my right angle and I draw an arrow straight across and label this side C, in example number 3, I actually have a value for C. Great. 15, I'll still call A. And so in this case, I don't know side B. We can still set up the same formula. So you can probably think of what the common mistake would be. Students get in the habit of just seeing two numbers and this number squared, the 15 squared plus the 17 squared equals some unknown squared. No. Make sure you label the triangles first so you can set up the formula. So we got 15 squared plus B squared. I don't know what that is. Equals C squared is 17, 17 squared. So this is going to be 225 plus, well, not squared, just 225, sorry, plus B squared equals 17 squared is 289. So B squared, when I subtract, I'm going to get 64. So remember, this is 225, subtracted this, so minus 225. I get me 64, so B is going to be 8. So 15 squared plus 8 squared equals 17 squared. And there's some other examples here, which I'm going to skip over now. And look at the bottom here. Some triangles have sides that are not integer lengths. So we're going to use what we know about simplifying radicals, if we can. So over here, same strategy. There's my right angle, straight across C. So I know that 3 squared plus 5 squared equals C squared. Well, this is 9 plus 25 equals 34. I'm sorry, it does equal 34. It equals C squared. So C squared equals 34. Take the square root of both sides. C equals root 34. In this case, I apologize, that's not the clearest. In this case, root 34 cannot be simplified. It's 2 times 17. Those are both prime. So this is my final answer, and I want to leave it in radical form. Okay, so when you do some of these where it doesn't simplify to a whole number like we had up here, right? These all 15, 25, 8 were whole numbers. Down here we don't have that, which is fine, but leave it in simplified radical form. Don't type in root 34 in your calculator and find some approximation that's going to be between 5 and 6. I want an actual number. This is exact. Okay, let's try a few more. Again, straight across. This is C. Always do that first, and then it doesn't matter which of the other two legs you do A or B. This is A, and this will be B. So 5 squared, A squared plus B squared, which I don't know, equals C squared, which is 12 squared. 25 plus B squared equals 144. If you'd like, you can subtract 5 squared from 12 squared right away, or write that over there, but I just like doing it this way. So B squared is 144 minus 25. That equals, 144 minus 25, 119. So B equals root 119. I can't think of any factors of 119, so I think we are finished, and this is exact. Lastly, we've got right angle, so this must be C. So we've got A, and this is B, and I don't know C. So 6 squared plus 10 squared equals C squared. 36 plus 100 equals C squared. So C squared equals 136. Sorry about that. That did not write as clearly as I would have liked. C squared equals 136. So C equals root 136. Now, this one looks like at least I could try to factor. So 2 times, well, I know 2 times 70 is 140, so 2 times 68. Okay, and this is 2 times 34. And this, I think we did that over there. We realized was just 2 times 17. So cross this off, cross this off, cross this off. So 136 is 2 times 2 times 2 times 17. 6 times 17. And is that right? Sorry, 8 times 17. 2 times 2 times 2, 8 times 17. Wow. And so I can circle this. These stay underlined so the 2 can come out. And 2 times the 17, 2 root 34. And you can check that too. Type in or take radical 136 and type it in your calculator and compare it to 2 times radical 34. Lastly, I wanted you just to be familiar, and you can hit pause. There's some really good shortcuts if you can remember what we call Pythagorean triples, which are super common right triangles. So you might see a 3, 4, 5 right triangle, a 5, 12, 13, an 8, 15, 17. Those are some of the most common. The 3, 4, 5 and the 5, 12, 13 are definitely common. But what's interesting is multiples of these are also Pythagorean triples. So if you can think of this as like A, B, and C, well, if I multiply each one of those by 2, I'd get a 6, 8, 10. That's also a Pythagorean triple. 6 squared plus 8 squared equals 10 squared. I could multiply each of my original 3, 4, 5 by 3, and I'd get a 9, 12, 15. 9 squared plus 12 squared equals 15 squared. And I could keep going on and on. Similar with 5, 12, 13. If I multiply, if this is A, right, B, the hypotenuse is always the longest, that's C. If I multiplied each one of these by 2, I'd get a 10, 24, 26. That is a Pythagorean triple. And I could keep going like that. But this is a super helpful tool. I would please put this in your notes. It'll save you a lot of time, especially on standardized tests. You can hit pause and put it in your notes if you want. And then lastly, we can still use, even if we have radicals, we can still solve for some of these. So this is A, this is B. So A squared is root 3 squared plus B squared, root 4, which is just 2 squared, equals C squared. Again, root 3 times root 3 is just 3. Root 4 times root 4 is 4, equals C squared. So C would equal root 7. And you could try some of these ones too. Let's do one more while we're here. This would be C, so this is A and B. Remember, always find that right angle and draw C straight across to make sure you always get the hypotenuse right. So we have 5 squared plus 5 root 3 squared equals C squared. Well, 5 squared is 25. 5 root 3 times 5 root 3. Let's do it off to the side. 5 root 3 times 5 root 3. Outside times outside is 25. Radical 3 times radical 3 is just 3. So that's 75. So obviously C squared equals 100. So C would be 10 in that one. Okay, so there's just a few examples, but that is day 1 with Pythagorean theorem. Hope everybody's doing well. Send me an email or a note in Schoology if you have any questions. Thanks.